Hey everybody, it's Electrollama. I'm here to show you a bit of a side project that I've been working on called OrbitSim. So I've made this program using Python, which is a well-known programming language, and with the matplotlib library, it's really simple to make plots where you can zoom in to different parts of the orbit and to individual bodies, like you can do in Kerbal Space Program. And it's basically designed to be as simple as possible, so anyone can hop onto the program and do whatever they want with it. One simplification is all of the orbits are two-dimensional, which basically saves you two variables. Also, there's no animation component. It just runs the numbers and plots the orbit. Now, one of the hard parts that I've taken care of already is when you have a flyby trajectory, because the math behind that is slightly altered from the simple elliptical orbit case, and those equations can be a little harder to find. So for example, if you have a school project where you need to do this, you can look at this file and sort of see what I did. But my personal end goal for this program is to create a game similar to Kerbal Space Program that the user can actually program themselves and perform missions using programs. So let me show you what I've done so far. The basic idea is the program reads numbers from a file. These are called the Kepler Elements, and these numbers fully describe an orbit. Here's a list of the elements that I chose to use in my program. Since I'm working in two dimensions, these are actually different from the standard Kepler elements, but most of them are roughly the same. But I had to be a little careful when doing this. For example, I couldn't use the apoapsis, which is normally the farthest distance from the parent body, because for a hyperbolic orbit or a flyby, this value would be infinity. So I just use the periapsis instead. You also have a few technical terms that all refer to angles, which are the anomaly, longitude, and the argument. Now, longitude is your basic polar coordinates measured from wherever you decide your x direction is. So here's a list of a few other elements that might be useful in different situations. My program can calculate these as well. When you open up the program, you'll see that there's a class called Orbit that has the Kepler elements as the instance variables. And if you need to calculate any of the other elements, there are methods or functions for that. And for the special cases of a flyby, there's a separate class for that, which basically overrides the orbit class. For example, an elliptical orbit is periodic, whereas in a flyby, you need the absolute time. One way that I tested my program is to change one of the orbital elements and see if it changes the orbit the way that I expect. So here's that test done with eccentricity, which is basically how stretched out the orbit is. And when you go beyond eccentricity of 1, it goes into a hyperbolic orbit, which you can see in the bottom picture. Here's the same thing with different periapsis, but the same eccentricity. And this is different longitude of periapsis, which is the direction of the periapsis. In my code, there's another class called state, which in physics refers to the position, velocity, and time of a particular object. One of the important features of my code is starting with an orbit and a particular time, you can get the position and velocity of that object. Conversely, if you have an object in space with some velocity, then you can calculate the orbit. Here's a test of having the same velocity, but at different starting positions. As expected, an object that's farther away with less gravity has a much broader orbit. In these plots, I'm changing velocity instead. So in the image on the left, it's basically if you were to burn prograde or retrograde, it goes into different orbits. With the image on the right, I'm testing different direction of travel with the same speed and position. So you can kind of convince yourself that these results make sense. So now that we have the orbits working, we can plug in the numbers to represent a system. So here's an example screenshot for the system in Kerbal Space Program. You can see it takes in the orbital parameters and also the size and color for the plotting. Here are some diagrams of the separation between planets being scaled down. So what's interesting is if you compare Kerbal Space Program to real life, they did a decent job just scaling down the solar system. With one exception that ELU is basically where Saturn would be. It would have to be much, much farther out to represent Pluto. And as a final check to see if everything was working, I plotted the real-life version of the solar system and compared to the diagram that was on the NASA website, and it looks like everything's working. So you can basically enter in whatever date you want, and it'll tell you the position of the planets and the moon at that particular date, which is kind of neat. Here are some of my future plans for the program. I want to be able to simulate spacecrafts as well, and simulate their burns to different orbits, and performing flybys, for example. And after that, I hope to make it an actual game where you can launch spacecrafts, perform different missions, and allow the user to basically program that mission. So I'm going to post this code on the internet, and that'll allow you guys to participate as well if you want to. I plan to make this a simple program so that even if you don't have a lot of programming experience, you can make reasonable contributions to this. So here's the link to the GitHub that has the program. You can try it out, you can use it for other projects, or you can contribute to make it more than what it is now. For example, you can help make this a game, or you can maybe develop it into a tool for Kerbal Space Program, or you can make maybe a stargazing tool. Right now it's at the point where it's flexible and you can use it for whatever you want. Alright, so I hope you guys will check it out, maybe download it, and maybe in a few months I'll post another video showing the progress that we've made. My name's ElectroLlama, and thanks for watching.